panelists include Professor Jin-Yi Tsai, Juris Hartmanis Professor in Computer Science, and Rajiv Ritu Batra Chair from University of Wisconsin-Madison. I think you guys should feel free to walk out. Professor Vedika Khemani, Associate Professor of Physics at Stanford University, and also the Execution Committee member of QFarm, which is Stanford's collaboration platform for quantum science and engineering. And Professor Jungsang Kim, Schiciano Family Distinguished Professor of Electrical and Computer Engineering, and Professor of Physics, and Associate Director of the Duke Quantum Center, also co-founder of IonQ. Professor Jungsang, Joan Reinhart Professor and Professor of Applied Physics at Stanford University, and the Director of QFarm, which is the Stanford's collaboration platform for quantum science and engineering. And the panel will be moderated by Professor Yi-Zhuang from the Physics Department of the University of California, San Diego, and the co-founder and CTO of EdenCode.
Okay, thanks. Thank you, Liang, and thank you, Liang, for the wonderful keynote speech. And many people here in the audience, I guess, is not from the quantum computing industry or field or research field. So maybe I think in this panel, I would like to take this opportunity to step back a little bit from the technical details and try to focus on some very broad questions. So I'm thinking about maybe three aspects of first of all, why quantum computing matters, and secondly, where does the field really stand today, and thirdly, like what should we look for in the next decade? So maybe let's start from the first question. So when many people hear about quantum computation, they just think it's like a magic, very mysterious computing device that can deliver a lot of computational power. But maybe quantum computing is not just about computation, there's more. So what do you think will be the most important impact that quantum computing will have on, for example, a broader scientific community or to our society? So maybe I start from Joan and then coming back.
Yeah, so I guess you spend enough time on the internet and you get pretty jaded and can convinced that maybe quantum computing will do everything, maybe it'll do nothing. It's very unclear. The way I like to answer this question actually is look back to like 2008, 2009, when deep neural networks were starting to discover cats in images. Right now, I'm a cat person, so I was excited about that for its own value. But if you weren't, you could understand that that's a hard problem, right? And that we should look more deeply into what neural networks might be useful for. And my view is that we're pretty much at that point right now with quantum computers. We have this example of factoring large numbers, which the large number enthusiasts are probably pretty excited about, but maybe many of the rest of you aren't. But that's a problem that's known very, very hard. And to me, that's the reason that we need to build quantum computers. When you have a new computational paradigm, like you can tell all kinds of stories about where you think it'll be useful, but until you have the device in your hands to play with, it's very hard to predict exactly what problems it's going to solve.
So I actually have a very exciting view of what future of quantum computing brings. I think there are some discoveries throughout the history that really changed the society at massive scales. The first we know is thermodynamics and physics, which led to industrial revolution with the steam engine. And then we discovered electricity, and we know how that has changed our lives. Then digital computation, semiconductors, that we know how that changed our lives. And then the internet, and then the AI. I think quantum absolutely has that potential to make an impact at the scales of complete transformation of our society. But again, if you ask me, am I here to predict the future? Because it may not, right? But I think a lot of that, it really depends on what all of us choose to do. If we can actually, find a way, find a path, and create the right technology, the right applications that are impactful to our lives. And then if a lot of investment goes into to furthering that technology, then something like Moore's Law happens, and then yeah, the world will change. So it's less about prediction, it's more about kind of what we choose to do. I think that's kind of where the real opportunity is.
I can maybe give a theorist's answer. So quantum mechanics is fundamentally how nature works. And having understood quantum mechanics, actually a lot of the breakthroughs that you were talking about, when we first understood quantum mechanics, everything that we take for granted today, whether it's LED screens, lasers, MRI machines, semiconductors, all of that has been built on the laws of quantum mechanics. And now what quantum computers are trying to do is up the level of that application to a much, much, much higher level of hardness. We're going to have to take systems of hundreds of thousands of quantum particles and figure out how to individually control and manipulate each of them. And then we're going to have to take these logical particles, which are emergent states of many, many of these particles, and figure out how to compute with these logical emergent particles. These are really hard problems. And to solve these problems, we just have to develop a level of conceptual understanding, which we don't have yet, which is really, really exciting, and which requires us to bring together insights from computer science, physics, math, engineering, and solving that kind of problem and developing those kinds of conceptual insights. I just don't see a world in which that doesn't lead to many, many downstream interesting technologies, just like the first wave of quantum mechanics led to the world that we live in today. So I think the future of technology will be quantum, and trying to build a quantum computer will get us there.
Okay, so I guess I'm slightly of more of a skeptic of quantum computing. And I'm from theoretical computer science. This is an exciting field, absolutely, tremendously challenging, and I admit, I concur with all my distinguished colleagues here about the challenges and opportunities.
What about your less distinguished colleagues?
My right estimable colleague will speak for. So this is, so speaking, we actually saw in your keynote speak about the Shor's algorithm. So I will just bring back, this was really a seminal moment, I think. In 1994, Peter Shor gave a quantum polynomial time algorithm, and that can factor large integers efficiently. And factoring is this problem where if I give you an integer, I want to find its prime factorization. So for example, 21 is 3 times 7, if I'm getting this right. 143, oh, I don't know, 13, 11. But so if the numbers are small, this is an easy problem. But when the numbers are huge, and this is where cryptography, public cryptography will depend on, the problem becomes extremely difficult. In fact, it's the presumed difficulty of large prime factorization that is at the basis of public key cryptography. So now, if Shor's algorithm says that if I can do these quantum operations precisely, then I can factor these large integers very efficiently and therefore would break public key cryptography. But if you look at it, the proof requires certain assumptions about these operations being exact. And maybe I'll show a slide I prepared a little later that basically I proved that if these operations are executed with even a vanishing amount of noise, even the noise level goes down to 0 when the number gets big, then Shor's algorithm actually provably does not work. I don't claim expertise on lots of other exciting areas that quantum computing could make an advance and impact. It's exciting one way or another, but I'll restrict my comments on that provable part. Liang, do you have any?
Yeah, so maybe first the answer to the previous comments. I would say maybe one thing that whether error correction could work highly depends on the noise model.
Yes.
And I think that we need to check what is the noise model used in your proof, that whether or not actually we will be able to design error correction to work. So there's a simple noise model that quantum computer wouldn't work, or even classical computer wouldn't work. It's power outrage, right? So everything gets out. So there are certain, we're not going to correct all the errors, but there are certain noise models. But currently we're being very careful with defining what a noise model is based on our knowledge of the physical platform. And we think that with the error correction, we'll be able to suppress error to high order without significantly increase the resource overhead. Yeah.
Actually, there is actually a standard framework that overcomes the challenge, because it is true that we have to make very, very small rotation angles that needs to be exacted for the algorithm to work. But I think the real magic there is discretization, right? So we actually can discretize the gates into a finite number of set of gates. There was a real interesting breakthrough in the late 2013, where people can actually approximate very, very small angle rotations with a logarithmic depth circuit with a finite number of gates. And that actually converts the small errors that you actually have to accomplish into a logarithmic depth circuit. And then you can actually count how many of those gates you need, and you just have to make sure that those gates that you run individually can actually reach that error level where the number is actually not exploding. So there is actually a fundamental theoretical model of how you disguise that model so that arbitrary errors can be overcome in doing exact calculation. But that does require, as Professor Liang indicated, you do need fault tolerance and make sure that you can get those very expensive gates to a certain level of accuracy. So I think fundamentally, I think there's a framework. Realistically, it's going to be extremely challenging and expensive to build such machines.
I would say if quantum computing doesn't work, it will be the most amazing measurement in validating quantum mechanics that we as a community have ever made. And actually, I was chatting with Jay Gambetta about this, who leads IBM research and also their quantum computing effort. And what he told me is that he got into the field actually because he was interested in these models of physics beyond standard quantum mechanics, and he really wanted to build a machine that was precise enough to measure the noise model accurately enough to find beyond quantum mechanical effects. He no longer is doing it for that reason, apparently, but I do think the real heart of the question is the noise model, for sure. Yes.
Okay, I think we heard a very interesting discussion about Shor's algorithm, and then the challenge that it has, and then maybe the future that we have to overcome these challenges. But maybe as an outsider or people from general public, they will ask, why do you want to build quantum computer just to factorize numbers? Why do you just want to break Bitcoin, for example, crash this financial market? That sounds very destructive. So do you think there's other more applications of quantum computing in different areas? Who wants to?
So I'll give one example. You know, the world is fundamentally quantum mechanical, which means that quantum computers are great at modeling the world. And so what this means is that there's potentially a wonderful opportunity to understand material science better, understand chemistry better, design better drugs, these sorts of things, based upon large-scale quantum computation, simulations of the way molecules form and interact with each other. And so I would say one of the most promising opportunities really is in simulating the world with quantum computers.
I'd say one more thing, which is like, I'm hard-pressed to think of a single time that humanity solved a really hard conceptual or scientific problem, and that didn't lead to all sorts of amazing technological applications that we hadn't envisioned. Like when we first came up with quantum mechanics, I don't think anyone thought that that was going to lead to transistors down the line. So this is such a hard problem, and solving it is going to require so many conceptual and engineering leaps that I think the fact that it won't have downstream consequences, I think it's almost like I just don't know how that would happen. Basically.
Yeah, I mean, it's really in some ways our modern Apollo program, to be honest with you, right? Like wire wrapping was developed for the Apollo program, right? And so like, I think, you're a theorist, you don't even know what wire wrapping is. Does anyone in the audience know what wire wrapping is? Okay, no. Just the two of us. Before people did printed circuit boards, they had little wires to connect the components together. Anyway, whatever. This is just to say, like, I think attacking the hardest problems you can find leads to all sorts of technological innovations beyond what you're trying to do.
I guess we can code JFK, right? We do hard problems because they're hard, and that leads to good things.
Yeah, maybe related to that, I think that in addition to quantum computing, I also mentioned there are other applications like communication and sensing and so on. Mm-hmm. And those actually can provide a resource which classically we don't have. For example, entanglement is a resource. And actually, like the Nobel Prize that can award it being experimentally verified that you get violation of Bell's inequality. And actually, by these violations, it's not just the fundamental research. It actually can be used for our coordinated, like situation like coordinated decision making. For example, two people came outside the light home, and they actually can, in certain situations, they can make a decision better with entanglement. So this actually provides a unique resource which we do not have classically, but we know we can harness the quantum system to actually help us to do something which is better. For example, maybe you want to arrange the power allocations, the power grid line, you want to do it as fast as you can. Maybe you can do this like a coordinated decision making that helps you to make a better decision.
So if I may speculate, go ahead. Go ahead.
So sorry, if I may, so just since error correction and fault tolerance was mentioned, and also in your wonderful keynote speak, I actually prepared a slide in the back, if someone could show that.
I don't.
So,
It's up.
yes?
No.
So quantum error correction code, and this basically brings up a theorem proved in theoretical computer science. It's called a threshold theorem, okay? And basically what it says is that if you can use more and more qubits to represent the one logical qubits, then you could imagine that you can use discrete operations like the T gates and pi over 2 gates to ward the noise away. So this is a formal statement of threshold theorem. But the theorem actually is proved under the assumption that the tensor product representation of one single qubit by arbitrarily large number of qubits by this tensor product framework is infinitely accurate. And in fact, that infinite accuracy implies that you have arbitrarily small angles, which I personally find hard if you look at the Schrödinger's equation and so on. There is, I believe this is now not something proved, but I believe that below a certain threshold, these are just mathematical models. They are idealizations. So you're pushing the non-existence or possible non-existence of arbitrary small angles in the SU2 group into this idea that tensor product is infinitely accurate. Yeah, probably now, this is a bit technical. Yes, but anyway, so my belief is that, the truth is in the pudding, and we'll see. The record is 21. That can be factored without, this quantum pre-processing and stuff. Mm-hmm. If it it's can good to be, have that would be great. Dispute. Thank you. For,
So if I may speculate a little bit, I'm going to actually walk into a little bit more speculative future. We talked about the world being quantum. That's very expensive to model classically. It's exponentially more expensive, so you can actually never do it with classical resources. I think there are some real interesting evidence when people started to build these machines and start to apply them to real world problems that people have brought to us. We're actually starting to figure out that there may be some real opportunity for machine learning as well, like AI. Because in many of these things, we actually collect data, and then we infer what the data actually means. We try to infer the structure within the data. There are many situations where a single event can lead to many measurement outcomes from multiple, because they're correlated events. And those correlated events, if you try to create a convolutional network and try to fit, you need a lot of data to fit it. Because convolution does not, these underlying correlations are not necessarily reflected in convolutional models. But with quantum mechanics, you can actually use entanglement or these quantum resources to create models that are fundamentally more correlated. And we have seen very strong evidence that you can actually start to fit these models with much of your parameters. Just like fitting a Hamiltonian is easy, it's just that the unitary unfolding of that Hamiltonian is extremely complicated. So we actually, I do believe that there is an opportunity where we can actually build in some realistic situations where the world is actually correlated events, we can build a fundamentally more efficient models that can be trained with quantum models more effectively. It's a speculation, but I think it's a huge opportunity. So there are things like that I think we have yet to explore. I don't think all of the...
So that basically means instead of factoring large numbers, quantum computer also probably may have application in maybe AI.
Absolutely, and quantum simulations, as we brought up. So there are many, many different opportunities there.
Okay, thanks for these wonderful discussions. And I guess we will have maybe left in 10 minutes. And does the audience has any questions want to ask? Yeah.
So my question is, dated back to 2019 when Google published the quantum supremacy paper. So the term that quantum advantage has been repeatedly mentioned. So in your personal opinion, how do you define quantum advantage? Thank you.
Anyone?
Yeah. Okay, maybe I can first start answering that question. So actually, like some of the papers that earlier when they say quantum advantage, I think the purpose for introducing this term is inspirational, so that people will be able to work in that direction to build larger systems. And now the subtlety is it's actually advantage compared to what? Compared to our state-of-art classical system, and we know the classical computer is also growing, so it's a moving target. And what happened is that also people developing more efficient classical algorithms to do it. And okay, I did talk a lot about quantum computing, and also part of my research is also to develop a classical algorithm to see where the boundary is. So I would say like during this process, we actually have a better understanding where the classical and quantum boundaries are. And the question actually becomes more challenging is if the system is noisy, right? Then it becomes like, okay, where the advantages are. But I would say like maybe from historical perspective, the role that the quantum advantage experiment is really to build the confidence that we do have some quantumness in our system before we really build the fault-tolerant quantum computing. And I would say like, okay, maybe once you build the fault-tolerant quantum computer, then I would say that probably we would worry less about how to define the quantum advantage, but because we really have harnessed the full power of a quantum system. Yeah, thanks.
So maybe I can take a step back. The definition that they had was really, can you do a calculation on your quantum computer, despite the fact that this computer is quite imperfect and it has a bunch of noise that you cannot predict the outcome of with any classical computer. Now, they made a claim in 2019 that they could do it, right? A lot of people took up the mantle, right? And the answer was, well, the algorithms weren't good enough on the classical computers, or the classical computers needed to get faster. It looks like now we've reached the point, I think, and we can see if others agree, that it's almost provably the case that these recent IBM demonstrations and Google are beyond the pale of what's possible, within 1,000 years on any classical computer we'd ever have. And the idea that makes that possible is that because a quantum system can be in exponentially many states at the same time, the calculation on a classical computer can take exponentially longer. And so just a little bit of improvement on the quantum computer can take it totally out of the realm of what a classical computer could ever hope to catch up to. Now, what I would say is, so that's what people mean when they say quantum supremacy. On the other hand, how many people here have disposals in their kitchen? So if you, cut up some food and put it down your disposal, and you try to simulate that with a classical computer, Navier-Stokes is a known hard problem, the physics of fluids and how they evolve, right? And so the counter-argument is, do we have garbage disposal supremacy? Like we don't talk about it in that way. And I think this is the counter-argument that cynics make to this. And at some level, they're not wrong. The proof is in the pudding, right? When you solve a problem that can't be solved anyway, that people actually care about, then you're in a much more interesting situation. We think that we're approaching that point, and what Liang was alluding to is the supremacy is not saying that we've done a thing that that's fundamentally important, but that it's the first time that we've made the quantum computer even do something that you can't do with a classical computer. And so that's why these benchmarks are relevant. And once we have the computers, the game is what can you do with them that's useful.
Maybe another question?
Hi, Ron. My name is Michelle. I work in the AI and biotech field. I have two questions for the panel. The first question is, where do you see the application of quantum computing in life sciences? That's the first one. The second question is that, do you see quantum computing has potential to replace classic computing, or do you think complementary to each other, like so can I have classic physics and quantum mechanics coexist?
Well, maybe I'll take a stab at that. I think in bio, again, there's a lot of correlated phenomena in bio, right? Let's say you have some fundamental problem with your health, and then it shows up in many, many different symptoms. And trying to see, and then if you can take those data to predict if you have, cancer predictors and things like that. Actually, one of my colleagues from grad school, she actually studied quantum measurement theory in the 90s, have become a biostatistician. And she actually has now started to use some of these quantum-inspired algorithms to actually create a very accurate predictors of cancer, for example, with very, very little limited data from maybe tens of people. If you try to do that kind of correlation using more traditional convolutional network, you need data from trillions of people, which we just don't have. So I think there are real opportunities if we open up our eyes and try to think about kind of the framework of some of these things from a very interpretable way. I think there's a huge opportunity. So that's kind of where I would put it.
Also, quantum simulation of molecules. So quantum simulation, I think, is one of the best applications of quantum computers that we know of. And a molecule is going to be a correlated system of many interacting particles. And so things like drug discovery potentially could be improved by being able to do quantum simulation. Then to your second question, I think we'll definitely still have classical computers too. It's not like a quantum computer makes everything exponentially faster. The problem has to have a certain structure in order to be able to exploit the superposition. Yes, if you want to build Excel spreadsheets to do stuff, a quantum computer is not going to help you with that. So, yeah.
TikTok will always be classical. Let me bring us back. I think Liang mentioned this earlier. Let's not forget about quantum sensing. And I think there are wonderful opportunities to make sensors that do less damage to tissue by using entanglement of photons and these sorts of things. An emerging direction that people are getting very, very excited about is what people call quantum computational sensing, which is to say, take sensors that measure at the ultimate limit allowed by quantum mechanics, and before you actually read the output of that sensor, which collapses its wave function, take that wave function and feed it directly into a quantum computer, okay? And then the quantum computer can process these correlated signals, if they are correlated, and make more precise measurements. So what I would say is, at some level, people call devices quantum sensors right up until they work. And then once they work, we just call them sensors, right? So like, you have quantum sensors all over your day-to-day life already, right? And just leveraging a little bit of entanglement is, I think, the next step. And my guess is that that is the first place that you will see, modern
In fact, we
quantum
have a whole
technology.
workshop on that next week at
Yeah,
Stanford.
in fact, if you're interested, QFarm has a quantum computational sensing workshop next week, and you're all invited. If you all come, it's going to be a little crowded, but Juna's in the front row. You can talk to her.
Maybe another question?
Okay, so hi, this is Amy Gao. I'm a 10th grade high school, so I may not be so good at the technical part, but I think you guys mentioned that quantum is also using machine learning. So I wanted to ask a quick question. how would quantum make machine learning more better, and probably what's the difference between quantum machine learning and just traditional machine learning?
Liang, you have to do that one. Come on.
Yeah, well, I think there could be different ways. Like, okay, we actually already using machine learning to help quantum. Like error correcting decoders, some of them are the AI decoders, which is actually like the fastest one. On the other hand, quantum can also like help with machine learning in a sense that there could be different ways. One is at the hardware level. Actually, our GPUs are not actually energy efficient. Maybe one can define like some like more efficient at the quantum level, those nonlinear units, so that it will be actually potentially be more energy efficient way to process information. And the other is actually like we're also looking into some of the quantum algorithm called HHL, which is actually a very efficient way to invert matrices. So if there are ways that you actually like lots of these gradient methods and so on, you could actually potentially use that to help you to speed up some of the things. But I would say that's still like a very like open-end research. We still like it's people don't know what exactly the answer will be. But I do see that there's potentially like some places that the quantum could help.
Actually, if I can comment on that a little bit from much more practical perspective. So the last technical team I built within IonQ before I left was the applications team. So we had an applications team. We had some preliminary quantum computers. And we had a lot of companies who came to us with their problems. And they didn't know quantum had a solution. So we actually started running these very conventional problems, right? Some of these are things like, how to identify a cat. We actually use like road signs. Can quantum algorithms actually do classification problems? Some of these were people looking for correlation in the data. Like they brought stock prices of Apple and Microsoft. And can you actually create a model that samples what that distribution looks like? So in all of these problems, they just brought the problem, not because they wanted no new quantum could help, it's the problem they had. And we actually built a lot of quantum versions of machine learning models, probably a dozen of them. And of course, all of these things are classical analogs. We have very powerful classical computers. Like if you try to identify cats and dogs, yes, quantum can do it too, but classical can do that pretty well. But the real insight we gained in trying to build these quantum algorithms and run them is really one of the things that Liang mentioned, is the efficiency. Energy efficiency is one, but I really think the real advantage is the data efficiency. Can you actually start, because we know people have been building the convolutional models for a very long time. It's only when we spent the last 30 years digitizing every language into a digital format, and now we can feed into it, we can actually have a decent accuracy to make LLM models work. There aren't that many situations where we have that kind of luxury in data. There are so many cases where you just don't have the data, and therefore applying LLM type model is just fundamentally not possible. There are problems like in healthcare models where there just aren't enough people on the universe to actually generate the kind of data that can actually fit. So if you can actually build some models that are fundamentally more data efficient, I think that can actually have a huge implication. And there are some signatures. I was speculating a little bit, but there are some signatures where quantum models can do that. We can actually infer to these quantum simulation models that in real quantum systems, that actually model works. Right? So the question is, can that extend to other types of correlated data we have? And I think that's a real opportunity.
Thank you.
Okay. Yeah, maybe one last question. Yeah.
Hi, this is Victor Huang. I'm doing a building a photonic computer instead of photonic quantum computer, like you guys say. So here is my question. What's the core difference between photonic computer and quantum photonic computer? And from the mechanics of physics mechanism point of view, of course, is the quantum computer must maintain the quantum entanglement, right? So there are two main families, if I'm not wrong, to maintain this quantum entanglement. One is the superconductor.
Maybe we can leave that technical discussion to afterwards.
Well, the other, okay. So,
given the amount of time, maybe one last question for all the panelists. Just in one sentence, is there a message that you wish the audience to take back? One
sentence.
One sentence.
Yeah.
Did that count?
can
No,
be wrong.
I just think now is actually the most exciting time that quantum science and technology have ever experienced right now.
Yeah, I think the fundamental difference between a skeptic and an optimist is just knowing what is fundamentally hard, what is fundamentally impossible, and what is technically hard. If you go back to 1960 and says we can actually put 10 billion transistors on a square inch of silicon at that time, there would have been a lot of scientists and engineers that was going to be impossible. So, but it's fundamentally possible. It's just technically very hard. I think we should be very open to take on challenges that are technically really hard but fundamentally possible. But try not to go faster than the speed of light until we have new physics. I think that's really hard to do.
Yeah.
I guess as a theorist, I'm very, very excited to figure out what's actually fundamentally possible. And understanding that has led to this real, information theory has emerged as this kind of unifying language across math, condensed matter physics, statistical mechanics. And that's just very exciting to me because there's, I think, a lot of fundamental physics and to be discovered.
What about Jin-Yi?
I think tremendous amount of effort went in and lots of money, a lot of wonderful people and smart, super smart people are into this. It's exciting, and my personal view is probably the most likely outcome is we're going to find some fundamental limit of what we understand today as quantum mechanics, where things break.
That would be great.
Lots of Nobel Prize for you, I'm sure.
Liang, do you have anything to add?
Well, I think that we are currently in the information age with big transformations. But actually, maybe we should think, is the information classical or quantum? Because quantum is the way that nature does.
Okay, thanks all the speakers.